Have you ever stopped to think about the absolute magic of a phone call? You say something, and almost instantly someone on the other side of the planet hears you. It feels so simple, right? But underneath, there's this incredible, lightning-fast journey happening. Today, we're going to pull back the curtain on the secret life of your voice as it becomes a digital signal and zips around the world.
So that's the big question, isn't it? How on earth does a simple sound wave, just a vibration in the air, get turned into data, shot across continents, and then perfectly rebuilt thousands of miles away, all in a fraction of a second? That's the puzzle we're going to solve together, piece by piece.
All right, so the very first, and you could say the most critical part of this whole trip, is the transformation. We've got to take something that exists in the real, physical world, that continuous analog wave of your voice, and translate it into the language of computers. Just plain old numbers.
And the technology that pulls off this amazing trick is called pulse code modulation, or PCM for short. This is the absolute foundation of pretty much all digital audio. Its job sounds simple, but it's brilliant. Take your analog voice and turn it into a clean stream of digital data, just a whole lot of ones and zeros.
You know, you can almost think of this diagram as a little factory for your voice. On the left, the raw material goes in, your analog sound wave. It moves through a few crucial steps on the assembly line, and what pops out the other side? Pure digital data, all packed up and ready to go.
So what's happening inside that factory? Well, it's a three-step process. First up is sampling. This is where we basically chop up the sound wave into thousands of tiny little snapshots every second. Then comes quantization. Each one of those snapshots gets a number assigned to it. And finally, encoding. Those numbers get translated into binary code. And boom, in just 3 steps, a physical wave has become pure computer language.
Okay, great. We've turned sound into data. Mission accomplished, right? Well, not so fast. There's a catch. PCM creates a massive amount of data. It's just huge, and if we want to send it anywhere quickly, we have to get a lot more clever. We've got to make this signal smarter, faster, and just better.
And that brings us to our next big challenge. How can we shrink this mountain of data way down without, making the call sound like you're talking through a tin can?
The solution is a really smart upgrade called differential pulse code modulation, or DPCM. Here's the genius part. Instead of sending the full data for every single one of those thousands of samples, DPCM just sends the tiny difference from one sample to the very next one. Because think about it, your voice doesn't change wildly in a millisecond, right? So that difference is a much, much smaller number, which means it takes way fewer bits to send. And you can see the key difference right here. On the left, you've got PCM. It's just a simple one-way street. But on the right, DPCM adds this clever little feedback loop with a prediction filter. The system is actually making an educated guess about what the next sound will be and only sends the tiny correction. It's way more efficient.
Now, what if we took this whole just send the difference idea and pushed it to the absolute extreme? Well, that's what delta modulation, or DM, does. It boils everything down to a single bit. That's it. All it tells the other side is one of two things. Is the signal going up or is it going down? A 1 for up is 0 for down. Talk about saving space.
And here you can actually see it in action. That smooth, curvy line, that's the original, real sound wave. And that jagged, stair-step line, that's the digital signal trying its best to keep up. It's just a series of tiny little steps, up, down, chasing the original. It might look a little clunky, but it is incredibly fast and efficient. So, now our voice is a super efficient stream of ones and zeros. But you can't just throw a 1 or a 0 down a wire, right? They're still just abstract ideas in a computer. The next step is to give them a real, physical body so they can actually travel. And this translation from idea to physical thing is called line coding. This is the process that takes our tidy sequence of ones and zeros and turns it into an actual digital signal, a series of real electrical voltage pulses. This is where our bits hit the gym and get some muscle.
What's so fascinating here is that there's not just one way to do it. All of these different squiggly lines are representing the exact same data, 1, 0, 1, 0, 1, 1. You've got different schemes using positive voltage, negative voltage, or no voltage at all to represent the bits. Each one is like a different language for electricity, and each one is useful for different situations.
Our signal is so close to being ready. We've converted it, compressed it, and given it an electrical body. But now it has to face its biggest challenge, the real world. And the real world is a messy, noisy place, so we need to bulletproof our bits for the journey.
I mean, think about it. Every wire, every radio wave is bombarded with noise and interference from all sorts of things. That interference can easily corrupt our data, flipping a 1 into a 0. And if that happens, the whole message can get garbled. So how do we protect against that?
The solution is just so elegant. It's a concept called error control coding. We take our original data, our message, and we add a few extra little check bits. You can think of these as a security detail traveling with the data. They're mathematically designed so that the receiver can not only tell if an error happened, but in many cases it can actually fix the error on the spot. So how do we measure how good this digital armor is? Well, one of the key ideas is something called Hamming distance. It's really just a measure of how different any two valid code words are from each other. The bigger that distance, the more robust your code is, because it's easier to spot when a bit has been flipped incorrectly and fix it.
And that right there is the final, crucial piece of the puzzle. This constant error proofing is what makes all of our modern communication so incredibly reliable. It's the reason the voice on the other end of the line sounds crystal clear, untouched by all the noise it traveled through to get to you.
So let's just zoom out for a second and appreciate the whole secret journey we've just followed. It is a truly mind-bending transformation that's happening millions of times a second all over the planet right now.
It starts as a simple wave in the air. It gets chopped up and turned into a bunch of numbers. Then it's made super efficient by just sending the tiny changes. After that, it gets a real electrical body to travel through a wire. Then it's wrapped in digital armor to protect it from noise. And finally, after all that, it arrives perfectly at its destination.
From a simple vibration in the air to a robust, self-healing stream of data, every single conversation is an absolute triumph of engineering.
It really makes you wonder, doesn't it? What other invisible journeys, what other amazing transformations are happening all around us, every single moment, all powered by these kinds of brilliant ideas?